What's NGC 346?
It's in the small Magellanic Cloud. It's a star-forming region.
Okay.
And it's actually an error here. I haven't started yet, but it's Webb, Chandra, and Hubble all mixed together.
Ooh.
I didn't give Hubble credit.
It's amazing how they can sync up. Okay. All right. Well, good evening, everyone. Welcome once again. Here we are at Sperry Observatory on the campus of Union College in Cranford, New Jersey. My name is Mary, and I'm a member of Amateur Astronomers Incorporated, which it's the astronomy club that makes its home here at the observatory. We're open every Friday night to the public, and we do streaming on YouTube and or Facebook when we can. So we give presentations every Friday night at 8:30 p.m. Eastern Time. Okay. You can find out a lot of information about us on our website, which is www.astrosm.org. And you can find out how you can join, how you can donate. You can find out the presentation for the coming week, what that presentation will be. Just a nice note that in 2024, Amateur Astronomers Incorporated is going to be celebrating its 75th anniversary as an astronomy club. And if you're a youth group or a small group, children's group, if you'd like to have a program, we provide them for those groups at 7 p.m. But you need to get scheduled. So you go onto our website and look and click on Join AAI, or click on the contact button, and that will give you information on how you can get scheduled for a program. Tonight's presentation is by AAI member Dr. John Sichel, who has been a longtime member of AAI. He knows how to operate our 24-inch telescope that we have here at the observatory. Plus, we also have a 10-inch refractor telescope. John also is a music composer. He teaches music at a community college here in New Jersey. He's given several presentations here at Sperry Observatory. And the title of his presentation this evening is The Latest from the James Webb Space Telescope. And with that, John, please take over.
Thank you, Mary. Hi, everybody. Excuse me while I fall on the floor, to quote Jimi Hendrix. The James Webb Space Telescope cost $1 gazillion and took decades to come to fruition. It launched about 15 years late on December 25th, 2021. Took about a month to get to its stationary L2 point orbit, and then additional months to be collimated, calibrated, cooled, and tested. NASA released the first Wow the Public images a little less than a year ago, and to everyone's relief, they were staggeringly beautiful. I showed some of them off in a talk last summer, and since then, Webb has released a slow stream of crowd-pleasing, beautiful images and accumulated lots of potentially game-changing scientific data as well, and I would like to discuss all of this in this presentation tonight. So Webb is an infrared telescope. It sees light in the infrared, meaning really that it sees heat. Think about standing by a campfire. As you back away, the warmth of the campfire drops off quickly. You can feel less and less of it. Well, this picture here of NGC 346, it's actually a composite image made by NASA's 3, I believe, surviving flagship space telescopes, Chandra, Hubble, and Webb. This is an object, a cloud, a star-forming region in the small Magellanic Cloud, which is a satellite galaxy of the Milky Way. It's about 200,000 light years away. So you're looking at the heat of a campfire, essentially 200,000 times 6 trillion miles away. And Webb is sensitive enough to feel the warmth, which can be translated into very detailed visual images. And because Webb is so sensitive, heretofore undetected information is a leitmotif running through almost every Webb image. Now, you may be wondering why, if Webb is so sensitive, it needs to have its data correlated with Chandra's data and Hubble's. Well, Chandra launched, first of all, Hubble looks at visual light. Chandra, launched back in 1999, is an X-ray observatory. It gives us very different information. So let's review a little bit about the electromagnetic spectrum. And there it is. With the exception of newly emerging data from our observation of gravitational waves with LIGO, all of our observing of the heavens from time immemorial is done through the medium of electromagnetic radiation. Any object showing any activity at all, that is anything warmer than absolute zero, is emitting photons. The more energy involved, the higher the frequency of emission and the shorter the wavelength. Those two factors are inversely proportional. Until the mid-20th century, all of our observing was done in the visual spectrum, which is really a very, because it's what we can see, it's really a very narrow band, though, of electromagnetic radiation. It's those objects that are hot enough to emit photons with a wavelength, if you believe this chart, about the same size as a paramecium. Then we began observing in radio waves, which are much longer wavelengths, and then we went to the other end of the spectrum, observing in X-rays and gamma rays, and then the cooler and longer wavelengths of the near, mid, and far infrared. All of these wavelengths show us different things. Infrared wavelengths, for instance, aren't really visible. Those in space are not really visible from Earth because they don't make it through our atmosphere, but they do a very good job of piercing intergalactic gas and dust, which means we can see things that are behind things, things that are obscured from our view with visual light. Because of that, though, the observations that are made have to be done at extremely low temperatures. So that's one of the reasons why the Webb Space Telescope is 1 million miles away and has a sun shield about the size of a tennis court to keep it from picking up any light. Observing in, any heat from the sun. Observing in all these different wavelengths offer different advantages and disadvantages. Like I said, Webb brings out unprecedented details in the lower energies of the infrared. Together, they offer a more complete picture of what's going on in an object. Let's go back for a second. Even if it is a bit different from what we would see with the naked eye. So for instance, there's a lot of gas and dust here. In the near infrared, you can see the stars that are behind it. This gas and dust itself would not be very visible in the mid-infrared. And objects that are emitting in X-rays wouldn't be visible necessarily to the naked eye, but are visible to Chandra. More likely, in reality, it's objects that don't appear so bright in visible light, but are much brighter in X-rays or in the infrared. By the way, when we look at these composite images, we see that some objects, a toy, some objects are brighter than others. That's why they sort of saturate the image. One sort of unforeseen trick here is that you can tell, looking at all of this translated into visible light, how these objects are bright. And that has to do with a effect of telescope building. When objects are very bright, they sometimes show what are called diffraction spikes, right? And it just so happens that these three observatories give you a different pattern. So this is something that's very bright in visible light, and you're seeing the Hubble image of it. If you don't see anything, we'll see plenty. Oh, here's one. This object here is very bright in the infrared, and it has the 8-spiked appearance that you get from the Webb. It's just a byproduct of the design of the telescope and where the struts are, and the fact that the mirrors of Webb are hexagonal, and so on. Chandra which is an X-ray observatory, has very strange special cylindrical mirrors, and I don't understand how they work. But so something that's very bright that doesn't show diffraction spikes at all. I don't see any in this image, maybe this one here, but you'll see them later on. Those are from Chandra when we look at a couple more collaborative pictures. So Webb design, you've all seen this. Webb looks a little bit like the skeleton of a Dalek riding on a luge. It's got sort of eliminate, right? And its most striking feature is this giant 5-layered sun shield, which again protects it from overheating. It needs to be kept at 447 degrees below 0 Fahrenheit, which is, excuse me, is it Fahrenheit or Celsius before it's Fahrenheit. That's about 6.5 degrees Kelvin. And so just a little bit warmer than absolute zero. On the Earth-facing side of the instrument are, as you can see, the antenna to communicate with Earth, the actual sort of drive systems, and the guiding instruments. On the top is, of course, the primary and the secondary mirror, and all the science instruments are packed behind the primary mirror, excuse me. Webb science instruments come from a couple of different sources. They come from NASA and the European Space Agency and the Canadian Space Agency. These two, they send us something other than smoke. These two diagrams show the physical grouping on top, how they actually are grouped on the back of the scope. And this one shows them more grouped by how they are supposed to be, how they are, basically employed. It operates in the near and the mid infrared from wavelengths of about 0.6 to 28.5 nanometers. The NASA contributions consist of the near infrared camera, which is critical for aligning the scope and can detect the most distant galaxies whose light has been redshifted into the infrared. And also a mid-infrared instrument called MIRI, mid-infrared imager. And that is good for looking at cooler objects like gas and dust, and for looking at, let's say, the atmosphere of an exoplanet and lensing the light that comes from the star behind it, so you can get some spectroscopic analysis of the makeup of the atmosphere. And then the European Space Agency instrument is a near-infrared spectrograph, or NIR-SPEC. That's NIR spec, right? Near-infrared spectrometer, which can take spectra of 200 objects simultaneously, which is pretty impressive, and thus analyze chemical composition and masses of targets. And then the Canadian contribution is a near-infrared imager and slitless spectrograph, which can be pointed with high precision for one of Webb's primary missions, which is what I just described before about taking the spectra of exoplanet atmospheres. This instrument is called MIRIS. Together, these three sets of instruments give Webb tremendous potential for both groundbreaking scientific discovery and those amazing pictures we've all seen and crave, although they are, of course, all translated from the infrared into visual light, so they're not what the objects really look like, right? This is something that frequently disappoints people, but they are showing the reality of the object. It's the same like when I teach music and I have to explain opera to my students, right? That opera is not realistic because people don't sing in real life, but it does present dramatic truth, right? And these present scientific truth, the images from Webb. All right, let's start with what I'm going to do is talk about a little bit about solar system objects, and then about stars, and then we'll go out into the galactic realm. Let's start with a relatively unspectacular picture of a comet. This is Comet Reed, which was first discovered in 2005. It's a representative of an unusual class of comets called main belt comets. Main belt comets don't come from where most comets come from, which is the Kuiper belt or the Oort cloud, but rather skulk about much closer to home in the main asteroid belt, hence the name, where they periodically show comet-like features, a halo and a tail and so on. This picture was taken on September 8th, 2022, and when the object was about 2 astronomical units away. This is the Webb equivalent of kind of looking at the end of your own nose, right, to look at something that close. It's an unspectacular picture because comets are basically just fuzzy things to begin with. So if you focus an amazingly finely tuned instrument on fuzz, it's going to look like fuzz, right? And yet, NIRSpec was able to learn something interesting about the main belt comets when it analyzed Read's spectrum. It was able to show that the tail and the halo of main belt comets come from pretty much the same process as the tails and the halos of Kuiper belt and Oort cloud objects, the sublimation of ices, leftover material from the beginning of the solar system. Comets are postulated to be one of the mechanisms that delivered water to the young Earth, and the spectrum shows that water is indeed present in comets' halo and tail. Let's look at the spectrum readings. What's interesting is that carbon dioxide, which is found in most Kuiper belt and Oort cloud comets, is missing here. You can see the bump right here, right? This is the blue line is Comet Read, and this is another comet. Oh, excuse me, the blue line is Comet Hartley, which shows the carbon dioxide bump in the spectrum, and Comet Read is the white line. It's, carbon dioxide is missing from main belt comets, perhaps because they are subject to the slightly warmer atmosphere, so quote unquote, of the inner solar system, or the comparatively inner solar system, and carbon dioxide sublimates at a higher temperature. So maybe that's why it's still present in comets from the outer belt. Here is a much more sort of spectacular picture. This is the Neptune system. Along with, you can see Neptune and several of its moons and its rings. All of its moons are named after sea gods and goddesses, fittingly enough, since it's called Neptune. I never knew, by the way, another music reference, that I never knew that Despina was a Greek sea god, a Roman sea god. I only knew her as a character from the wonderful Mozart opera Così fan tutte. And Larissa, as far as I knew, is my boss's secretary. So I'll have to ask her the next time I send in like the next annual report if she's also a sea goddess, but I'm not sure she'll appreciate that. So the interesting thing about this picture, there's a lot of interesting things about it. First of all, how staggeringly beautiful Neptune is in the infrared, but how bright Triton is. And look at the this is a perfect example of the 8-spiked diffraction spike pattern from Webb. 6 large spikes and 2 small ones. Again, deriving from the hexagonal shape of the mirrors and the struts. So you might think that Triton, because of this picture, that Triton is hotter than Neptune, but it's not. It's actually much colder. It's one of the coldest places around. It's at about, in the solar system, that is, it's at about minus 391 degrees Fahrenheit. That's cold enough that the nitrogen in its atmosphere condenses and coats the moon with a really reflective frost. And that's why Triton is so bright. What you're looking at is sunlight that's being reflected rather than absorbed by Triton. It reflects actually 70% of the sunlight that hits it, making it much brighter than Neptune. So let's get that pesky bright moon out of the picture, something we're always doing here, right? Trying to get rid of the moon in our images or in our telescopes. and focusing on Neptune itself, it's the same picture. There's another reason why Neptune is much darker than Triton, not only because Triton is very bright and reflective, but Neptune is particularly dark in the infrared because methane in its atmosphere, which is fairly common in its atmosphere, absorbs red and infrared light, which is why it gives Neptune its overall bluish tinge. There are some bright spots in the atmosphere. You can see them here. They correspond to high altitude clouds where the methane has frozen into crystals that are, again, highly reflective. There's also a very bright area around the North Pole, which is just over the rim of the picture. And there's a storm at the South Pole, a vortex. People knew about that vortex, but this shows that it's surrounded by a ring of clouds as well. Which again shows that high altitude methane. And then as for the rings themselves, they're barely detectable in the visible light. I don't think we knew about them until about the 1970s or so, because they have a much higher concentration of organic components like methane than, say, Saturn's rings. But they are very beautiful in the infrared. Okay, so let's move out to the stars. And let's start with, I love globular clusters, as some of you might know. They're like my favorite objects in the sky, purely for the ooh-ah, they're gorgeous type of reasons. They're clusters of more or less, well, they are more or less spherical. If you've ever looked at a globular cluster in the telescope, they contain something on the order, typically, of about 500,000 stars. And they're densely packed to the point where they're gravitationally bound. So they never, open clusters will eventually over time drift apart. Globular clusters are stuck like this, and they're very ancient objects. So most of them have been together for a long time, unless they get ripped apart by the gravity of a galaxy or something. They're mostly old, like I said. The stars are very low in metallicity. Remember that metal to an astronomer means anything that's not hydrogen or helium, right? So those were the elements in the original universe, and everything else that's in the universe was created inside of stars and then belched out into space when, one way or another, the stars came to the ends of their lives. But these clusters are very low in metallicity because the stars are all basically first generation stars. They're interesting, both boring and interesting for that reason, on the way. Every galaxy has attendant globular clusters. The Milky Way is surrounded by a halo of about somewhere between 200, 225 of them. Andromeda has more. I think M87 in the Virgo cluster has something like 10,000 globular clusters because it's so enormous to begin with. And you could sort of make the case that it's in itself such a gigantic globular cluster. But M92, which is what we're looking at here, is in the constellation Hercules, which has made it sort of overshadowed. It's a very beautiful cluster, but it tends to be overshadowed by the fact that the premier northern hemisphere globular cluster, M13, is just a couple of degrees away, also in Hercules. In this image, the core is covered up by a chip gap, basically, in NIRCom's receptors. That's the near-infrared camera. And also because if it weren't obscured, the core's bright cluster, which you can see in this Hubble image, would make all of these outer outskirt stars kind of impossible to see. And you're distinguishing between individual stars here in a cluster that's 27,000 light years away. I believe that, you know, I don't believe, you could sort of imagine how chaotic the orbiting of these stars is. It's all around their common center of gravity, but they're probably like baby penguins in a creche, right? Sometimes they're on the outside, sometimes they're on the inside. you can only imagine what the sky would look like if you were somewhere in the middle of a globular cluster like this. Those of you who were science fiction fans, there's a famous old science fiction story from the old days called Nightfall by Isaac Asimov. It was like his first big hit, supposedly was inspired by his wondering about that question. So let's look at, just focus in on the lower left quadrant of M92. Why do astronomers want to focus on these giant clusters of very aged stars? Well, according to the Webb team scientists, one of the reasons is that all of these very aged, low metallicity stars formed at the same time, which is between 12 and 13 billion years ago, and all are more or less the same distance away, 27,000 light years. So because of that, they have only one critical variable between them, which is their initial mass. So it's a great way of studying stellar evolution when you have a population of stars that are all the same except for differences in their mass, basically. Webb is sensitive enough to detect individual stars in this cluster, from giants down to dwarfs less than a tenth the mass of the sun. It also makes it easier to constrain the whole cluster's age. With no annoying variables, you can just see where the constituent stars leave the main sequence, right? Verge off on that Hertzsprung-Russell diagram, and then do the math, and you can figure out the age. One other reason for observing M92, because the stars are so densely packed, studying it allows scientists also to test and refine their ability to pinpoint measurements when dealing with objects very close together. And that's a very important ability to be used in one of Webb's primary missions, which is exoplanet observation. Let's go to the other end of the spectrum. Globular clusters that we were, like the one we were just looking at, are like the astronomical equivalent of gated communities, right? This is a picture of what you don't find in gated communities, which is the youngins, right? This is a protostar called L1527, or more accurately, I think L1527 is the name of the dark interstellar cloud that Webb was able to penetrate with its infrared vision, creating a sort of stellar ultrasound of a baby star system still kind of huddling in its midst. The star itself is hidden by a narrow black band right there. And that black band is a protoplanetary disk, the site of a future stellar system. The orange and blue vortices above and below the stars are being spun up by the accelerating rotation of the star itself, which is flinging gas and dust outwards into what is already a cloud of gas and dust around it, and therefore heating it up. All of this is invisible except in the infrared. And here's another young, slightly older young star, one that we're much more familiar with. This is Fomalhaut, which is a comparatively close by star, about 25 light years away. And it's pretty easily seen and found on autumn nights when here in New Jersey, it's virtually the only star visible in its part of the sky, which is the south. So you see lots of bright stars up here. There's Andromeda, there's Pegasus, there's Aries, and down there there's one star, and that's Fomalhaut. It's in a constellation called Piscis Austrinus, which means the southern fish. It's otherwise, all of the rest of that constellation is much too faint to be seen. Fomalhaut is only about 440 million years old. And if that sounds silly or funny, the sun is about 4.5 billion years old, right? So that's 1,000 times older. And shows a very dense disk of gas and dust orbiting around the star, which has been blotted out with a coronagraph, which Hubble has on board, so that we can see the outer rims. What's interesting is if you look at this spot right here, and there's a close-up inset, you can see something forming in those outer bands. These are maybe like an asteroid belt and a Kuiper belt kind of in the process of forming. What's this? Is it going to be an asteroid, a planet, a dwarf planet? Starbucks, I don't know. But it's one thing you can guess is that if you look at it, you can see the size of it here. That's 80 astronomical units on the scale bar. So this is gigantic. But probably as it's in the process of coalescing, it's going to be shrinking as it coalesces and becomes more dense. But it's kind of neat. It's a snapshot of a solar system in its very early youth, a stellar system, I should say. Now here's the other end of the spectrum. These are Wolf-Rayet stars. They are at the other end of the timeline, I should say, from stars like L1527 or Fomalhaut. These two are called WR140, this guy over here, and WR124. You can see that it's very bright in infrared. Wolf-Rayet stars are extremely massive stars that have burned through their hydrogen and helium and are now burning basically whatever elements they have to hand. They need more hotter and hotter temperatures as they burn heavier and heavier elements, and they are trapped in sort of a cycle of expansion and contraction. What happens is that as they expand, the temperature gets cooler and cooler, and they can no longer fuse whatever is left in their core. So gravity takes over, and they start to contract, and that causes the core to heat up until it becomes hot enough to burn whatever's there, and then it expands again, and so on and so forth, almost ad infinitum, but not quite. And when they bounce back out, they sort of spew off their shells of the outer atmospheres, and you can see that kind of vividly, especially in this picture. That's really impressive, right? You can see the periodicity of this star's pulsations in the infrared, when you can see those lines of gas and dust. These paroxysms continue until all that's left in their core is iron, or there's a lot of iron left in their cores. And iron has the problem of costing energy when it fuses. It uses energy up rather than creating it, which means that there is nothing to stop the star from contracting. And then it bounces back in a spectacular explosion, and you have a type 2 supernova. This can only happen with very massive stars. That's what awaits these Wolf-Rayet stars, and their stories, like I said, can be seen in these pictures. You can get an idea of this cyclical pulsation and spewing out of shells of gas and dust. And then comes the kaboom, right? So this is Cassiopeia A, a remnant of a type 2 supernova that is thought to be the last galactically local supernova to have been visible naked eye from Earth. It exploded during the 17th century, as it appears to us, 17th century Earth time, since the star is 11,000 light years away. It would have been 11,000 years plus the 17th century, or subtracted from it. And scientists calculate that it should have been visible in about 1667 or thereabouts. The only problem is there isn't any record of it. In 1680, the British astronomer royal John Flamsteed, who's famous for having made a pioneering star atlas, Flamsteed recorded a 6th magnitude star roughly where the remnant can now be found, but no one else duplicated his results. And intriguingly, in 1630, observers in Britain observed a noonday star, quote unquote, which was understood at the time to herald the birth of Charles II. But given the vagaries of human nature, my first impulse is that the noonday star was more likely a case of political propaganda, compounded by mass hysteria, or something that doesn't happen anymore. Again, this traces in the infrared light the tendrils of gas and dust. This is just a detail. If you've ever seen the whole supernova remnant, it's also very spectacular. And then one more time back to what stars look like even before they're born. This, I don't know why, but I think this is like the most beautiful picture from, I think it has to do with the coloration. This is an object called the Chameleon-1 dark molecular cloud. It is in the constellation of the Chameleon, which is not a very bright one. We don't get to look at it. But it's a picture of what stars look like before they born or even really conceived. Paradoxically, stars will only form in really cold gas clouds because they need less of a gravitational nudge to get started contracting in a rotational way that is required to eventually create a star. The wispy clouds of gas are lit up by a protostar. So there is a young star here called CED 110 IRS4. I love these poetic names, which is the bright orange object, again, in the upper left. Importantly, the clouds are also lit up by the stars behind it, which we can see because of near count. And the reason why that's important is because this backlighting enables Webb's spectroscopic instruments to analyze the absorption lines in those stellar spectra, and then we can find out what's in the cloud. So this image was very, very out of focus. It took me a long time to read some of these lines here with the words, but the gas is mostly hydrogen, of course, but it's the dust that's interesting. The spectra shows absorption for carbon dioxide, carbon monoxide, acetaldehyde, ethanol, methanol, methane, carbonyl sulfide, and particularly strongly, water, among other things. So give it a few billion years and we could really cook up something. And then here is sort of the whole stellar circle of life contained in a close-up view of the heart of the Tarantula Nebula. The tarantula, when I type fast, I transpose letters and I have the Tarantula Nebula over and over again. It's going to make me crazy. But the Tarantula Nebula is one of the largest star-forming regions known in the universe. We can't see ones that are super far away, so we don't know. But it takes up a fairly significant percentage of another satellite galaxy of the Milky Way called the Large Magellanic Cloud, which is larger than the Small Magellanic Cloud, which orbits and is gradually being sort of torn apart by the Milky Way about 170,000 light years away. I suspect the tidal forces of our galaxy are stirring up the Large Magellanic Cloud and driving its star formation because it's forming stars at a feverish rate. You can see the gases from which the new stars are being formed, plus several hot young stars and the whole star cluster over here. And plus there's a few, again, this has gotten the image of the projector is a little out of focus, but there are some faint galaxies visible in the background, which is something you get really used to with Webb images, looking at the little galaxies you never knew were in the background. Of course, we in New Jersey don't get to look at this because smoke and fog and rain and smog and light pollution aside, this is deep in the southern hemisphere in the constellation called Dorado. So why does the Webb scope have the capability of observing in both near and mid-infrared wavelengths? You'll get an idea of it if you look at these two pictures taken by Webb of the Tarantula Nebula. One is the one we just looked at. This one over here, you can see how it corresponds, and you can see how it's different. Some of those background stars are hardly visible at all, but much more detail of the gas and the dust is visible. This is the mid-infrared, that's the near-infrared. And scientists creating the images can balance them as they see fit. Now here's another question. The Tarantula Nebula is in another galaxy, albeit one very close by. So I'll use it as a segue to look at some galaxy pictures. We're all used to seeing these images from the Hubble and Webb Space Telescope of the deep field, the very deep field, the ultra deep field, the oh my God deep field, right? The I can't believe it's not butter deep field, whatever. And so on. And we're used to hearing these mind-numbing factoids like the field of view is the size of a paramecium's nostril seen from the International Space Station or whatever. And we're also used to hearing that all of these little objects are galaxies. So that the only stars in the picture are the much nearer Milky Way stars, and they can be easily identified because they're so much brighter by their diffraction spikes. I ask you, which of these galaxies is the one closest to the Milky Way? Anyone want to take a guess? The surprise answer is we're actually looking at all these stars and galaxies through the stars of WLM, which is a dwarf elliptical galaxy, or maybe with a name like WLM, it's like an AM radio station. But it's about 3 million light years away, which is a little bit further away than the Andromeda Galaxy. But these are all stars in the galaxy, with plus the light of other galaxies behind them. So you're looking at individual stars, again, in the galaxy 300 million light years away. There's a nice little video here. This is a zoomed out image, of WLM. And we were looking at this part right here. And if I play this little video, you can see that. Right, and then that's the image that we were looking at. So WLM as a dwarf galaxy is the stars are packed less densely, which makes it easier to separate all of these individual stars, as well as the galaxies that are in there. And here's a real famous galaxy. Now, I think this is going to back up first before it goes forward. Yeah. Here's the Cartwheel galaxy. Also in 2 pictures from Webb. It's also known as ESO 350-40 and PGC 2248, depending on which catalog you look at. It's about 500 million light years away in the southern hemisphere constellation of Sculptor. The picture on the right is taken in the near infrared, taken with NIRCam, and the picture on the left is taken in the mid-infrared with the MIRI instrument. Up until about 440 million years ago, it says, our time, this galaxy was probably a normal spiral like our own, but then it got T-boned by another galaxy not visible in these pictures. These 2 little galaxies are considered part of this object, are called G1 and G2. G3, which is the perpetrator of the hit and run, is off in this direction somewhere. Now, the cartwheel is, well, it's a cartwheel. You can see it's got an inner ring and an outer ring and spokes, right, connecting. It earns its name, and it's the result, again, of having a galaxy go essentially through it. It's a fire with star formation everywhere, as you can see in the MIRI image. There's hot gas and bright clusters of stars all around the galaxy. Again, the effects of sort of gravitational trauma in a way. The nearest of its companions, G1, is also undergoing starburst, but the more distant one, excuse me, this is the MIRI image. The more distant one, G2, shows almost none, and it's quite amazing in this picture how you can even barely see it. In this picture, you can see a little bit of a tail being pulled by gravity off in this direction from G1. And these 2 pictures, again, show just how much we can learn just by looking at the same object in different wavelengths. Also, note the difference between this this. I'm not sure what they are, but in the infrared, it's very bright. Excuse me, in the mid-infrared. So that's the cartwheel. And now here's a cartwheel in the making. This is an object called ARP-220. ARP is the name of a famous book. It's the ARP Catalog of Peculiar Galaxies, which kind of sounds like a animated cartoon on Nickelodeon, right? Or Cartoon Network. It's about 250 million light years away, so about half as far as the cartwheel. And it's in our hemisphere for a change, located between Corona Borealis and Serpens Caput near Ophiuchus. This is two galaxies caught at the moment of collision, in flagrante delicto, if you will. You can see this tremendous amount of infrared energy caused where the two nuclei are interacting, causing a bonfire of star formation. There are apparently about 200 new star clusters in an area about 5,000 light years across. So think about that for a second. That's as much gas also in that area as can be found in the entire Milky Way. The cores of these two galaxies are about 1,200 light years apart, which makes you wonder if a spectacular merger of supermassive black holes is also on the menu in the next few thousand years. Also, as per earlier radio astronomy, about 100 supernova remnants have been found in an area of only about 500 light years. So if you want to imagine the night sky in that part of the universe, if any planet in that part of the universe is left habitable, that would be kind of an impressive place. ARP-220 is classified as an ultraluminous galaxy, which means a galaxy with a luminosity of greater than 1 trillion suns. It is, in fact, the nearest ultraluminous galaxy to the Milky Way. But in some short amount of time, the nearest ultraluminous galaxy to the Milky Way might just be the Milky Way, when in about 4 billion years, it and the Andromeda galaxy do this. We'll see. At some point in the process, it might look like that if we're around in 4 billion years to have a look at it. And let's sort of finish with a couple of pictures from where we began with collaborative images. This is Webb teaming up with Hubble to show an image of a pair of galaxies called VV191. These galaxies are not interacting, they're superimposed. So from our vantage point, the spiral is passing in front of the elliptical galaxy. This is also another stupendous picture. Plus, of course, you've got all these little galaxies in the background, and there's a galaxy right there that's being lensed. It's way in the background, but it's being lensed by the elliptical galaxy, which is kind of neat. This is a good example of what the difference is between elliptical galaxies and spiral galaxies. Spiral galaxies are very active still. They have lots of star formation, and you can see it all. These are all hot clouds of gas and bright young star clusters. Nothing going on there, just a bunch of old stars in sort of the galactic equivalent of Boynton Beach. So this is going to be a much larger galaxy. You can see that it's larger in the picture, but it's also further back, so it's quite a bit larger than spiral. And here's another beautiful composite image of a barred spiral. This is Webb and Chandra. This is, and also Hubble, I think. This is NGC 1672. Yes, because there are some Hubble objects right there, these diffraction spikes of stars in our galaxy. So this is Webb, Hubble, and Chandra, infrared. visual and X-ray observations. This is a beautiful barred spiral galaxy. A barred spiral galaxy has an elongated bar in the center, and the spiral arms come off of that. It's found in Dorado, where the Large Magellanic Cloud is, about 50 million light years away. Here, the blue-white objects with the north, south, east, west diffraction spikes are again from Hubble. These purple dots that are scattered through, they're from Chandra. They're objects that are extremely bright in X-rays, and what they likely are pulsars and black holes that are feeding. That's an interesting image because it gives you some idea of how they're distributed in the galaxy. We can see some that are sort of covered up, but they're just visible. So there's several of them there. They give us an interesting picture, again, of how populated the galaxy is with things like black holes or pulsars. And the infrared imaging of Webb shows us in detail where the gas and the dust are. So we get a view of where the star formation is going on. Whatever that X-ray object is causing a great deal of star formation right in there. And one last picture on my farewell slide. This is NGC 7496. By the way, NGC, you don't know, it stands for New General Catalog. This was a catalog made by Sir John Herschel, who was the son of William Herschel. William Herschel made a catalog of objects called the General Catalog, and his son updated it and created the New General Catalog. Along with the usual gas, dust, and star formation that Miri shows, this one also shows us an active galactic nucleus. You can see how bright in the infrared the nucleus of the galaxy is. It's thought that this is basically that the supermassive black hole at the center of NGC 7496 is sort of at the equivalent of an all-you-can-eat buffet. It's ingesting a lot of stellar matter, but it's a wonderful, a beautiful image, and it shows how much is going on in these galaxies. If we were, Milky Way is not as extreme a barred spiral as this galaxy, but if we'd be like out here somewhere, we wouldn't know that and don't know that much about what's going on in the center of the galaxy, although we know a lot more than we did thanks to this kind of viewing in other wavelengths. Which brings us to this quote, which I like at the end. The universe is like a safe, in which there's a combination, but the combination is locked in the safe. Right? We're always trying to get closer to that. So with that, come to an end of the presentation. Thank you all for coming. Does anybody have any questions? Thank you. Any questions out in the audience or from the online people? I can't hear you. All right.
Not talking.
Yes.
Yeah, the near infrared and the mid infrared. I mean, is it literally like near, like closer?
Closer to the visible light.
Closer to
So the near infrared are the shorter wavelengths of the infrared. The far infrared are the longer wavelengths of the mid infrared. So if I go back to that that slide at the very beginning. So right, the near infrared is basically here, and mid and far. Okay, so let me just inform you that next week's presentation will be by Cliff Ashcraft, and it will be called My Astronomical Journey. We're dialing in tonight from Boston, so that might be part of this astronomical journey. So thank you again, and see you all next week. All right, let me. Yep. We good.
Thanks for. That's your eyes.